Hi guys, in this class I would like to discuss about galvanometer, how galvanometer works. So what is the working principle of galvanometer and how this galvanometer is related to our concepts and what is the use of the galvanometer, what can we find by using the galvanometer. So we know that so far we discussed about magnetic fields and current carrying circuits in the presence of magnetic field. And to understand this concept, I would like to recall or you just do a quick revision about torque acting on a current carrying loop in a magnetic field. We got that expression torque tau equal to N I B A sine theta. So this expression we are going to use to derive the torque. Torque means the deflection, what is showing in the galvanometer. And we can identify what is the exact the reason how this technique or this working principle we make use to measure the galvanometer in the given circuit. So let us see what is this galvanometer. Galvanometer is an electromechanical instrument which is used for detecting and indicating an electric current. So far we know about voltmeter and ammeter. Yeah, voltmeter is used to measure the potential difference and ammeter is used to measure the current in the given circuit. And here galvanometer is like that meter only, but it detects and identify the presence of current. And it is so sensitive. It's so sensitive electromagnetic device. It can measure very low currents or the order of the microamperes. So it works more accurately by producing a rotatory deflection in presence of electric current flowing through a coil. It contains magnetic field. So as per I said, the moving coil is rotating in the presence of magnetic field, so that causes the instrument galvanometer works. So let us understand the construction of the galvanometer. To construct a galvanometer we need two concave magnets, and apart of that we need a rectangular coil which can be held with a support. And the rectangular coil having conducting wire, that conducting wire obviously having certain resistance. So here remember the galvanometer is also having certain resistance. I can make use of that sentence later. Again I am repeating it here. The coil is wounded with several turns of wire, conducting wire, because electricity has to pass. And this wire, conducting wire, having certain resistance. So altogether this resistance is only we call as galvanometer resistance. And this coil is supported with two supports on the top and down as pivoted. So just like pivot, it gets supports. And over that we need to use very important thing at here, a coil spring. A coil spring is mounted both ends, upper end and the bottom end. So without this coil spring, so the galvanometer needle, it won't come back. So just like a coil spring help us to get the needle come back. Suppose when current passes, what happens? The circular coil rotates. So when circular coil rotates, so when current gets off, now it has to come back by its own. So with the help of the springs, so it gets restored. So here the springs plays a key role, and we insert at here on the rectangular armature a cylindrical magnetic material. So this cylindrical magnetic material, so inside the rectangular armature, a cylindrical magnetic material is used to increase the strength of the magnetic field. And that entire setup is placed between the two permanent magnets, and here the very importance of the concave shape of the magnets, because concave shape of the magnets always gives the radial magnetic field. So then only the galvanometer can able to rotate evenly. It means the torque should act on the coil uniformly. So to the purpose only, the magnetic field should always be radial. Radial means perpendicular. So that we can see by doing some calculations. And here over the galvanometer, to measure the torque with the deflection, we need to use a scale. So this scale helps us to read the deflection in terms of the measuring scale. So whatever the deflection happens in the rectangular coil, so that deflection we can measure just like a scale at here. So it can able to measure how many divisions is deflected. Means here we can say that as a particular word known as angular deflection. So with the help of the scale we can measure how much needle is deflected by passing how much amount of the current. And when circuit is connected, so the circuit is connected through the two ends of the rectangular armature. When current is passes, the deflection takes place. So that deflection will be seen on the galvanometer. So here the important thing is that the working principle. The working principle is a current carrying coil placed in a magnetic field. It experiences a torque. So that's the key point at here. That's why this concept we are studying in this chapter. A current carrying coil experiences a torque. Yeah. So this is a rectangular coil which placed in the uniform magnetic field. When current is passes through this rectangular coil, through the side AB and from the another side from the C to D. Now because of the interaction of the current with the magnetic field, so there is a net resultant force will be act at the two ends on the AB and the CD. Yeah, of course another ends they both gets cancel each other, but these two ends, the force at these two ends is equal and opposite in direction. So this force will act on that equal in magnitude and opposite in direction. So this is the two equal forces acting oppositely causes a couple and with the perpendicular distance it causes a torque. Now that's the reason, depends upon the magnitude of current, the deflection takes place in the galvanometer. Now, so to prevent higher deflection here, the coil plays an important role to bring it back the needle. So when current passes the rectangular armature rotates, it experiences a torque, and to get it back there should be a restoring force. The restoring force which is developed by the spring. Now the spring gets back the needle to its original position. So that's the importance of the spring at here. Now if you can see, the mathematical expression for torque. So how we can write express the torque? The torque for this case, torque tau equal to force times perpendicular distance. Torque tau equal to INBA sin theta. Now here you notice that to deflect torque uniformly, everything should be constant. Yeah, if I see current I in the coil is constant, and N number of turns also constant, and B magnetic field is also constant, but A is area vector, it is also a constant. But what about theta? So here our task is to make theta should be constant. So how this theta element is coming? Theta is nothing but, so this expression comes from the A cross B, IN times B bar cross A bar. It means the magnetic field interacting with the area vector. Now, if the magnetic field interacting with the area vector, if we make such an arrangement, if it interacts always with perpendicular, if it can able to interact always perpendicular, so then the term theta always should becomes 90 degrees. Suppose if I take it here, 1 second. Yeah, here our task is to make the tau equal to NIBA sin theta, and the angle theta should be always 90 degrees, even though the armature rotates. Suppose if I take here the needle, right now here needle is not showing. Suppose if I take this as needle, so this needle always should be perpendicular to the magnetic field. Here the needle means nothing but the area vector of that rectangular armature, and needle is mounted on it. So to make the area vector always perpendicular to the magnetic field, so then the terms at here everything will becomes 90 degree. So now tau equal to, if N is constant and I is constant and magnetic field B is also constant, if theta is always 90 degree, then torque is uniform. Torque tau equal to constant. Yeah, to make the area vector always perpendicular to the magnetic field, so the the natural magnets here are curved as a concave shape. Now our final expression is satisfied at here. The tau in this expression, if we can write that tau equal to NIBA. Again I am repeating it here, so please keep it in mind. The area vector of the rectangular armature always perpendicular to the magnetic field lines. So then only the torque, uniform torque will be acts. Not only that, the torque is also constant. And now in this expression, what is the dependent factor? Now to a galvanometers, we cannot change always number of turns, and magnetic field also cannot change, and areas also do not change. The only dependent factor of the torque is only current. So when current increases, automatically the deflection in the galvanometer is increases. So that is the needed. So when current increases in the galvanometer, so the deflection is obviously increases. So that makes to measure the current by using the galvanometers easily. Let us try to derive the mathematical expression for this. So if I write the expression for torque tau equal to b naught sin theta, that equal to n I b a sin theta. So here theta is always 90 degree. The tau equal to maximum, that equal to n I b a. So this is the expression for torque. Now, so the torque tau deflects the coil through an angle alpha. Then a restoring torque is set up in the coil due to the elasticity of the springs. Because of this torque, the needle will deflect. If the deflection is taken at an angle alpha, that's known as angular deflection. If torque deflects the coil through an angle alpha, the same deflection can be done by the springs. The springs should play a key important role. So we can write the expression for the torque tau. This is the restoring torque. Restoring torque. So this is due to springs. This torque is due to spring. The restoring torque is also directly proportional to alpha. So here alpha is angular deflection, or you can take simply angle. Now we can take proportionality constant, the tau restoring equal to, we can introduce a constant k, a little k, small k times alpha. Now tau restoring force equal to k times alpha. Here k is spring constant. K is spring constant, or we term as torsion constant. Spring constant or torsion constant, both are same. Now we know that the restoring torque equal to deflecting torque. So restoring torque equal to deflecting torque. So this restoring torque is due to springs. It is due to springs, and it is due to current in the rectangular coil. Current in the rectangular coil in the presence of magnetic field. Here the two torques are there. One torque is due to current interacting to the magnetic field that causes force at the two ends of the rectangular armature, and that causes to deflection in the rectangular armature. A counter torque will be acts to bring back the needle. So that is due to because of the help of the springs. Now for the restoring torque, here we got that two expression. Restoring torque equal to k times alpha, and the deflecting torque equal to b naught, n I b a. So what we got the expression at here, tau. So this we term as a deflection torque. So this is, we can write this as a deflecting torque. This torque is due to deflection of the armature in the presence of magnetic field. Now let us make it equal. Now we need to find that alpha. So that is what is the angular deflection? Alpha equal to n IBA times K. So here alpha is nothing but angular deflection. What is the angle which is deflected due to the current carrying conductor in the presence of magnetic field? And if you can see in this expression, alpha contains mostly constant. So here n equal to constant, and B magnetic field is also constant, and area A is also constant, and K spring constant, it is also constant. But here the one and only variable is I. If current changes, the deflection in the needle also changes. And we can write this in terms of as alpha equal to this total terms, we can replace that as 1 over G. 1 over G times I. So here G equal to capital G, galvanometer constant, little k upon, it is little k upon NBA, which is known as galvanometer constant. So from this expression we blindly write that the angular deflection alpha is is directly proportional to current I. So through the galvanometer, how much current flows, so that much angular deflection can be seen. So when current is more through the galvanometer, obviously the needle will be deflect more. So that deflection we call it as alpha. So the deflection produced in the galvanometer coil is proportional to the current flowing through it. It is a very, very important statement. And the factor here, the factor G equal to K upon NBA is a constant for a given galvanometer. If the galvanometer having different ranges, sometimes it is having a range of 0 to 30, or sometimes it is having a range of 0 to 50. When you can see in the laboratory, that we can understand it. So galvanometers are having the different ranges. So here that range is depends upon this factor G. Here the G we call as galvanometer constant. Galvanometer constant. Galvanometer constant capital G equal to K upon NBA. Or we use a different word which is more important than the galvanometer constant, which is known as figure of merit. Figure of merit, galvanometer constant or figure of merit. So this figure of merit is a constant for a given galvanometer. We need to do some experiments to find out that. So let us identify the figure of merit a little more. Suppose if I rewrite this following expression, the same expression what I am having at here. So if I can write that as alpha equal to 1 over G times I. Now from this we can write the expression for G equal to I times I upon alpha, which equal to capital K upon NBA. So which is known as figure of merit. So from here we need to define two more definitions, small definitions. When it comes to galvanometer, as per we said that it's a very sensitive device. It means it can able to measure very low currents, very feeble currents. So that we define in terms of sensitivity. Sensitivity of a galvanometer, of a G meter. Let me make a shortcut. Sensitivity of a G meter. A galvanometer is said to be sensitive if it shows a large scale deflection even when a small current passes through it, or even when a small voltage passes through it. Yeah, if it can able to show a large deflection for a even small milli amount of current or millivolts or the voltage, that we define as sensitivity of the galvanometer. So we can write here current sensitivity. Current sensitivity, I suffix s, if we can write that is alpha upon I. Here alpha is nothing but angular displacement. Alpha equal to, we got it the alpha value at here. If I can do that calculation, NBA upon K, just you do the reciprocal of it here. So here we already having I upon alpha equal to K upon NBA. Just if we do reciprocal at here, we need to get that current sensitivity is NBA upon K. Now if you can notice, this current sensitivity is directly proportional to number of turns and strength of the magnetic field and area of the rectangular coil, and current sensitivity is inversely proportional to, I suffix s, is inversely proportional to spring constant. So the current sensitivity, to increase the sensitivity of a galvanometer, you want to make a very sensitive galvanometer. What are the things to be done? So increase the number of turns, or increase the strength of the magnetic field, increase the area of the rectangular coil, or decrease the spring constant. So what is the use of the current sensitivity? It can able to measure very sensitive currents under the order of milliamperes or the microamperes. And here I would like to define one more, that is voltage sensitivity. Voltage sensitivity. Voltage sensitivity, V suffix S equal to, if we divide alpha upon V. So how we can define alpha? We know the alpha value. So alpha upon, from V I can write that V equal to IR from Ohm's law. So the above expression going to change as, and we already knowing the value of alpha upon I, NBA upon K, and in the denominator extra terms will be added, NBA upon K times R, little k times capital R. So the voltage sensitivity is also directly proportional to the three factors, number of turns and strength of the magnetic field and area of the cross section, and inversely proportional to two factors right now. One is the resistance of the coil. Yeah, galvanometer is having a coil inside. So that coil is made up of a conductor. Obviously conductor having resistance. Not only that, here the K is known as torsion constant or the spring constant. So these are the two factors, which is, one is current sensitivity and another one is voltage sensitivity. Not only that, here we define figure of merit or the galvanometer constant, G equal to, that is also one more important formula, G equal to the current upon alpha. Here alpha is nothing but the deflection constant, at what angle it is deflected. So G equal to I by alpha, so K upon NBA. So all of these are the very small formulas, and they are very important, and they are giving us confusion. But to get rid of your confusion, just remember the very important equation to derive this entire expression. As per my suggestion, this is the equation. What is that? The restoring torque, it is due to springs, which equal to the deflection torque, it is due to current in the rectangular coil. If you can just remember this equation, the rest of the things will becomes automatically.